The first part, we show how to compute the WG finite element solutions. Okay, the WG finite element solution can be found by solving the equation 17 here. So in the following, we are going to perform the error analysis for this special element here. That's for simplicity. Now, this means V0 is approximated by case-order polynomial. VB is approximated by case-order polynomial. And weight gradient is approximated by K-1 polynomial. So since we use same order polynomials for V0 and VB, then our stabilizer looks simpler. We don't have that QB there. Okay. So by solving equation 17, we can find UH. So next, we're going to see how this WG solution approximates the true solution, U. So first, we define three L2 projections. Q0 is the L2 projection to the PKT. QB projects to the PKE. We use same order here. And the page L2 projection to PK-1T to the D's power. Okay, here we are D equal to 2 for 2D. For the 3D is the same thing. Okay, weight gradient definition is here for this special WG element. I put the definition here for our next, we define a triple bar norm and the QHU. The triple bar norm is also called the energy norm. It's induced by the bilinear form A here. But this one really is H1 equivalent norm. And the QHU, remember U is our true solution. QHU belongs to VH, which means it's a wake function. It has two parts. V0 part is a Q0U, is the L2 projection to the PKT. And the VB part is QBU, project to the PKE. So QHU is approximation of U, which we know the difference of those two, because it simply is its L2 projection. So our goal next is to estimate QHU minus UH, the error in the energy norm and in the L2 norm. Here the double bar means L2 norm. Okay, first of all, we need an important identity, equation 19. Equation 19 here means U here, you can think about your true solution. Equation 19 means QHU, roughly say it's the L2 projection of U. Take away gradient of it. It's approximation of gradient U. It's L2 projection of gradient U. In other words, weight gradient QHU is a good approximation of gradient U. So the proof of this lemma 1 is simple. What do we need to do? Just using definitions of weight gradient and the QH. Okay, by equation 18, which is the definition of weight gradient, then the left-hand side equal to this one is V0. For this QHU, the 0 part is a Q0U. Then VB is a QBU. Q0U, as long as this function, I mean divergence of Q, is a degree of polynomial, is a polynomial with a degree less or equal to K, then we can take a Q0 out, which Q there is K minus 1. You take gradient K minus 2, obviously less or equal to K, less than K. Therefore, we can take Q0 out. Similarly, we can take QB out. This is L2 projection on the boundary. So then we got this second line. Then the second line, you use integration by parts. And we cancel this term, we cancel second term and simply become this. And since Q there is K minus 1 polynomial, look at it here. Therefore, we can insert this pi h here. Pi h is pk minus 1. Therefore, we prove the equation 19. For simplicity, we introduce this standard notation. Since we cannot take derivative over the whole omega, so we do that on each element t, then add them together. So this means area integral, and this partial t is a line integral. Okay, our important identity, I just copy here. And our weight gradient definition is a copy here. It's easy for us to derive this sense. Okay, so we introduce this error term, we call it LUV. LUV equal to this sense, defined in 21. We introduce this notation just like for simplicity, because we don't have to write this whole sense every term. All right, so now let's see the lemma 2. Lemma 2 is like identity 23. So let's prove that. First of all, we need to know the fact. Gradient u dot n times the VB. We integrate on each partial t, then add together. That gives you 0. That's because the VB take a single value on E, and the gradient u dot n is continuous. So they cancel out for the interior edge, and the VB equal to 0 on the boundary of omega. Therefore, this whole thing is 0. All right, now let's start first line. So the first line, we got the first line by using integration by parts. Then, since V0 is case order polynomial, gradient of that is K minus 1. Therefore, we can insert this pi h here, L2 projection. Then we're using identity 20. Then this ends become to this one. And then the second term, since this one equal to 0, so basically we minus 0 here. All right, so next, we do integration by part for the first term. So we got a V0, then divergence this term, then V0, this sends dot n, and copy the second term. Okay, from here to the next equation, what we did is add this term and subtract this term. Then combine these two together. If you look at the equation 22, this gives you the first term. Let's simply use this one, simply use the definition of weight gradient. Then combine this term and this term, give you this one. Then copy the last one. Then combine those two. That's exactly the definition of LUV. So we proved lemma 2. Okay, so in this slides, we will derive the equation, the error term satisfied. We want to estimate the difference, QHU minus UH. For simplicity, we'll give a name, we call it EH. So EH is also a wave function containing two parts. Q0U minus U0, QBU minus UB. The first part is, this first part is really is E0. The second part is EB. Okay, equation 24 is a WG, finite element formulation. I just copy here. All right, so UH satisfy equation 24. We know that before. So lemma 3 give us the equation we call the error equation. That means the equation error term EH satisfied. So now let's derive it. By lemma, first of all, we multiply Poisson equation, both sides by V0, then integrate it. So by lemma 2, the left-hand side equal to this, equal to right-hand side. That's the result of lemma 2. Then we substitute this right-hand side to 26. We got equation 28. Then next one, we add the stabilizer term on both sides of the equation. We got a 29. And this sense really is A QHUV. So QHU satisfy equation 29. So we make a difference of 29, use 29, subtract 24. We derive our area equation. This is FV0. FV0 canceled, only have those two terms. So we derive our area equation 25. Okay, finally, we're ready to estimate the difference of QHU to UH by triple bar norm. Okay, I copy our area equation here. It's 31. Then we have lemma 4. Lemma 4 gives you an estimate for the two right-hand term of equation 31. I will prove lemma 4 in the next slide. Let's just use it first. So we have theorem 1. Theorem 1 there, U is a true solution. UH is a WG solution. Then the difference of those two in triple bar norm, we got, which is H1 equivalent norm. We got H to the kth power, which is the optimal order. Let's prove it. So what do we need to do in the error equation? Let V equal to EH. V equal to EH, then we have AEH, which is the definition of a triple bar norm. And the right-hand side is LEH, SQHUEH. Then by using lemma 4, we got the right-hand side. Then we divide the triple bar norm of EH. We prove the theorem. In other words, QHU minus UH, the energy norm is H to the kth power, which is optimal order convergence. Okay, now let's quickly prove the lemma 4. One, the error analysis for the WG DG method, anything with discontinuous polynomials. This inequality 35 is called a trace inequality. It's very important. We can use all the times. So now let's prove lemma 4. So the first term, stabilizer. So by definition, we got this one, then use a Cauchy-Schwarz inequality. Then the first term, we use a trace inequality. We got those two terms. Then the second one, just copy it. So the trace inequality, Q0 is case order, is L2 case order projection. So this one, L2 norm, give you HK plus 1 order. So they cancel that, give you K. The second one is H1 norm for the case order approximation, give you K. So we got this. The second one, by definition, is a part of a triple bar norm of V. Similarly, we can estimate LUV, also case order. Here we use the L2 projection, H, which is K minus 1. It's a L2 norm, so give you K. So we finish the error estimate for, then we prove this theorem. Okay. The error estimate in triple bar norm is case order. Now let's look at L2 error estimate. This is standard duality argument. Okay. I missed something here. Okay. I'm sorry about that. Here should have like comma QBU minus UB. Okay. So as I said, E0 is the first part. Okay. So that's what E0 is. E0 is Q0U minus U0. So this is the dual standard procedure, and we're assuming H2 regularity, means solution to norm is bounded by right-hand side. All right, here I copy the lemma 2 results. It's equation 43. We're going to use it. And also the error equation, we're going to use it to derive the following. Okay, then we have the theorem 2. The theorem 2 there uses two solution, UH is WG solution. Then it's a L2 error estimate of HK plus 1, which is the optimal order. So to prove that, what we need to do is same thing. Multiply this equation, both sides, by E0, then integrate it. So E0 give you E0, the L2 square, then give you this one. For this sense, we use lemma 2, we use the equation 43. That U equal to phi, and the V equal to EH. Then, by using equation 43, we got a second line. So the next one, we're going to add SQ to phi EH and subtract it. We're going to add and subtract. Then those two terms give you A, EH, QH phi. Then copy those two terms. A, EH, QH phi. A, EH, V here is QH phi. So let V here equal to QH phi. Then we got those two terms. Then keep the last two. So next, we will bound this 1, 2, 3, 4 terms. That's similar to the proof of lemma 2. I will skip that here. So if you want the detail, I suggest you to look at the paper in the following. So finally, we can, here we use the H2 regularity, equation 42, replaced by E0L2. Then we prove theorem 2. Okay, so we prove the error analysis for the WG method is very straightforward and simple because our formulation is simple. Okay, the last slides we have some useful website. You can find some code in those two websites. Thank you.